Hello everyone and welcome back. So far we have acquired quite a bit of a knowledge about the floating point numbers. So in this particular session we are going to observe some solved problems on those concepts. So without any further ado, let's get to learning. Coming to the outcome of today's session, today we will first observe a series of linked problems. And thereafter, we will end the session by learning the summary of floating point representation. Consider this question. Suppose a 16-bit register of the following format is used for storing binary floating point numbers. The mantissa m is denoted using normalized sign magnitude fraction, and the exponent e is expressed in x64 form. Now, as you can see, there are 5 different questions linked to this particular concept. So we will try to solve them one by one. So let's begin with the first question itself. How many bits are used for the fractional mantissa? So let's try to solve it. Now if you notice, here we are talking about a 16-bit register, aren't we? Now in that particular 16-bit register, we know we are going to assign the first bit of the bit pattern, that is the MSB, as the sign of that particular number. Now notice carefully, the exponent e is expressed in x64 form, right? Therefore, the x64 bias is used. So from this we can determine one thing, that is the maximum negative value, that is the minimum value to be really honest, is going to be minus 64. Now minus 64 can be derived from minus 2 raised to the power 6, because 2 raised to the power 6 is nothing but 64. And we can also write this down in a different format, that is minus 2 raised to the power 7 minus 1. So clearly, 7 bits will be used for the exponent portion. Now in this particular question, we are supposed to find out how many bits are used for the fractional mantissa, that is this particular portion. So let's calculate that. The total size of the register is 16 bits, correct? 1 bit will be assigned for the sign bit, and we have just found out that the exponent is of 7 bits. Coming to the mantissa part, it's definitely going to be of 8 bits. So this is the answer to this particular question. Basically, 8 bits are going to be used for the fractional mantissa part. Let's now move on to the second question. What should be the expression for the decimal value? Basically, we are trying to figure out the formula using which we can convert the data stored inside the 16-bit register back to decimal. So let's try to solve it. Now honestly, in our previous sessions, we have already seen that there are 2 different ways we can perform the normalization. One is explicit normalization and another one is implicit normalization. And we also have learned that the implicit normalization form is more precise than the explicit normalization form. And since nothing has been mentioned in here, so we can rightfully assume that implicit normalization is being used. So clearly, this formula, that is the formula for the implicit normalization, will have to be used in order to find out the decimal values. Now why it is implicit? Observe, for the mantissa part, we are having 1 point and then the mantissa. So this is the specific reason why we are going to denote this as the formula for the implicit normalization method. Now for this particular question, we can be a little bit more definitive regarding this formula. And how is so? Observe, the exponent, that is the biased exponent, is going to be expressed in x64 form. Therefore, the bias is 64. So the formula which will be specific to this particular question is going to be minus 1 raised to the power the sign bit multiplied by 1 point mantissa multiplied by 2 raised to the power the biased exponent, and we should negate the bias, that is 64, from the biased exponent. So this is the expression which will help us retain the decimal value. Let's now move on to the third question. What is the largest number in base 10, that is in decimal, that can be represented using this register? So let's try to solve it. Now we just have figured out this is going to be the formula using which we can determine the value stored in the register in decimal, can't we? Now coming to the register, we already have seen it is of 16 bits. First bit is going to be assigned for the sign bit, next 7 bits are for the biased exponent, and finally mantissa is going to be of 8 bits. Keeping this organization in mind, let's try to determine the largest number. Now since we are talking about the largest number, therefore the sign bit for that particular number is clearly going to be 0, signifying the positive magnitude. Now the mantissa is of 8 bits, therefore 1 followed by radix point, and thereafter in that mantissa part, we are going to have 8 ones since we are trying to figure out the largest number. Now let's figure out the exponent portion. So yes, it will be the base of 2. Now think about the biased exponent. It is of 7 bits. Now using 7 bits, if we place all ones in the 7 bits, we are going to have the value 127. Now how did I determine that? Think about it. If we are talking about the 8th bit from the LSB towards the MSB, that will have the place value as 2 raised to the power 7. That is 1 less than its place's number. So that will be 2 raised to the power 8 minus 1 or 2 raised to the power 7, which actually is 128. So if the 8th bit is giving the place value as 128, all the 7 bits before that combinedly is going to give us the value 127, isn't it? Now from this particular value, we are going to reduce the bias, that is 64. Now this will give us 1. So we will end up having 1.81 multiplied by 2 raised to the power 63 because 127 minus 64 is 63. Now let's get rid of this radix point. So in order to get rid of this, we need to place it at the end, right? Now if we do that, we are going to reduce the value 8 from our exponent, which will give us the value 2 raised to the power 55, correct? Now just for the sake of uniformity, let's convert this 2 raised to the power 55 into 2 raised to the power 50, and thus we will have to append 5 more zeros by the end of this sequence. Now if you remember, during the session conversion to decimal, we learned that during the conversion of a big binary bit stream to decimal, instead of converting that directly to decimal, we actually can take help from a number system of bigger base. So for that, we will be using hexadecimal in this particular case. Now how to convert a binary bit stream to hexadecimal? It's pretty straightforward. All we have to do is start combining 4 bits from the least significant bit towards the most significant bit. So let's begin the process. So this is the first set, and in hexadecimal it is going to be 0 because 4 zeros is nothing but 0, right? Consider the next set. This is 1110 or 14 in decimal, E in case of hexadecimal. Coming to the next set, 4 ones, clearly F. Now we are still left with 2 more bits, right? Now just for the sake of uniformity, we need to convert it into a set of 4 bits. So that's why we are appending 2 more zeros to the left. And thus, this particular set is going to retain the value 3. So this binary bit stream in hexadecimal is 3FE0. Let's now convert that into decimal. Now in order to convert this into decimal, we will need to multiply the place values with the proper decimal representations of all the symbols. So let's do that. Now 3 is going to be 3 in decimal as well. Coming to F, it is actually 15 in case of decimal. Now the hexadecimal symbol E is 14 in case of decimal. And 0, it is actually 0 in all the number systems. Now let's multiply the respective place values. So we are going to multiply 3 with 16 raised to the power 3. Now F, which is 15 in decimal, is going to be multiplied with 16 raised to the power 2. Thereafter E, which is 14 in decimal, is going to be multiplied with 16 raised to the power 1. And finally, the least significant hexadecimal digit, that is 0, is going to be multiplied with 16 raised to the power 0. And the result of this entire operation is going to be 16,352 in decimal. Now, since we have converted this entire bit stream of binary in decimal, we also need to figure out the exponent part. Now, if you notice, 2 raised to the power 10, that is 1024, is almost close to 10 raised to the power 3, that is 1000. So, using this approximation, we can say 2 raised to the power 50 will be pretty close to 10 raised to the power 15. You are getting it, right? 2 raised to the power 10 into 5 is actually 10 raised to the power 3 into 5, and thus we get the value 10 raised to the power 15. So in terms of decimal, the value is going to be 16,352 multiplied by 10 raised to the power 15. And this is the largest number in base 10 that can be represented using this register of 16 bits. Let's now move on to the fourth question. What should be the bit patterns for 7.5 in decimal and minus 16.125 in decimal. So let's try to solve it. Let's take the first value, 7.5. It is a positive number, right? Therefore, in the sign bits place, we are going to place 0 only. Now let's try to figure out the rest of the bits, shall we? Now 7.5 in decimal is going to be 111 radix 0.1 in binary. Now why so? 7 in decimal is 111 in binary, and 0.5 in decimal is radix point followed by 1 in case of binary. Now we already assumed that we are going to use implicit normalization form. So using that, if we place the radix point in this place, that is the right hand side of the first one in the bit sequence, observe, we are actually moving the radix point 2 bits towards the left. And that is the reason why as the exponent we are having the value 2. Now remember, this is going to be the biased exponent, not the true exponent. Therefore, in order to calculate the biased exponent, we will require the true exponent, that is 2, and thereafter we will need to add that value with the bias. So the biased exponent is going to be 66. Now observe, we have 7 bits for this exponent field. Therefore, the bit pattern to be saved in that exponent field is going to be 10000010. Now why is that? Because the MSB holds the place value 64, that is 2 raised to the power 7 minus 1 or 2 raised to the power 6. And with that 2 raised to the power 6 or 64, we are going to add the place value 2, that is 2 raised to the power 1, which will eventually give us the value 66. Now can you guess the mantissa part? Observe, after the radix point we have 3 ones. So we will simply place that. Now coming to the rest of the cells, we already know we can fill it up with zeros. So this is going to be the pattern in this 16-bit register, which will represent the value positive 7.5 of decimal. Let's now figure out the pattern for minus 16.125. Since it is a negative number, clearly in the place of sign bit, we are going to place the bit 1. Now we already have figured out the sign bit. Coming to the magnitude, that is 16.125, if that only is converted into binary, observe, the bit pattern is going to be 1 followed by 4 zeros, followed by radix point, then 001. Now how did we determine that? Observe, this bit is going to have the place value 2 raised to the power 0, that is 1. This has the place value 2. Then this one has the place value 4. Thereafter, this bit has the place value 8. And finally, the MSB will have the place value 2 raised to the power 4, that is 16. So that is the integer part, which is 16. Now coming to the fractional part, that is 0.125, it actually is 1 by 8, which is the place value of this particular bit, that is 2 raised to the power minus 3. Now this is just the basic binary representation, right? We need to convert this into implicit normalized form, and you already know the drill for that. All we have to do is place the radix point at the right hand side of the first one in the bit sequence. Now in order to place it in here, observe, we had to move the radix point 4 bits towards the left, and therefore we have the exponent as 4. Now let's figure out the biased exponent. We need the true exponent, that is 4, and then we will add the bias, which will give us the value of the biased exponent 68. Now in the exponent field, we are going to have the bit sequence 10000100. Now why is that? Similar to the previous one, here also this particular bit has the place value 64, and this one is placed in the place value 4. So 64 plus 4 will eventually give us the value 68. Now coming to the mantissa part, we have 8 bits for that, don't we? Now let's count the bits in the fractional portion. 1, 2, 3, 4, 5, 6, 7. So these 7 bits are going to be placed in here. Now coming to the last bit, we know we can fill it up with 0. So this is going to be the bit sequence which will represent the value minus 16.125 of decimal in the 16-bit register. Let's now move on to the fifth question. Determine the difference between the smallest positive number and the second smallest positive number in this representation. So let's try to solve it. Now this is going to be the formula which we will use to determine the values of the smallest positive number and the second smallest positive number. So let's begin with the smallest positive number first. Now since we are talking about positive numbers, clearly the sign bit is going to be 0, right? Now we are talking about the smallest number. Therefore, in the exponent field, we are going to fill it up with all zeros. Now coming to the mantissa part, we also are going to fill the bit places with zeros only. Now let me show you how this will be represented in decimal. So since the sign bit is 0, we will have -1 raised to the power 0 multiplied with 1 because we are using the implicit normalization method. And thereafter we will place all the mantissa bits, that is 8 zeros in here, which will be multiplied with 2 raised to the power 0 minus 64. Now why 0? If you observe, all the exponent fields are filled with zeros. And that is why we are having the biased exponent as 0 only. Therefore, the value is going to be 1.0 multiplied by 2 raised to the power minus 64. So this is the smallest positive number. Let's now figure out the second smallest positive number. Now this also is positive, right? Therefore, the sign bit is going to be 0. Coming to the exponent part, this is also going to be zeros. However, in case of the mantissa, we are talking about second smallest positive number. And that is the reason why in the mantissa part, we are going to have the value all zeros followed by the last one in the LSB's place. So since the sign bit is 0, we will have -1 raised to the power 0 multiplied with 1 followed by the radix point, then 7 zeros followed by a 1 in the LSB's place, which will be multiplied with 2 raised to the power 0 minus 64. So we will acquire the value 1 followed by radix point, thereafter 7 zeros followed by 1 multiplied by 2 raised to the power minus 64. So this is the smallest number and this is the second smallest number. Now if you try to find the difference, observe, we will be left with 0.00000001 multiplied with 2 raised to the power minus 64. Now let's try to get rid of this radix point. In order to do so, we need to place this radix point by the end of the sequence. So basically, we will have to move the radix point toward the furthest right. And for that, we are moving the radix point 8 bit places towards the right, and therefore we will have another exponent 2 raised to the power minus 8. So finally, the difference is going to be 2 raised to the power minus 72. And this is the difference between the smallest positive number and the second smallest positive number. Now with this result, we have come to the end of our series of linked questions. Let's now follow the representation of floating point numbers summary. So basically the floating point numbers are stored in mantissa and exponent form. Thereafter the notations represent mantissa as normalized sign magnitude fraction, right? Because if you remember, for mantissa, we actually dedicated the most significant bit of the entire bit stream for representation of the sign. And coming to the mantissa portion, we have seen that the values are stored in implicit normalized form, haven't we? Thereafter, the normalization can either be explicit or implicit. However, we usually go with the implicit normalization form because that provides us with more precision. Then, the exponent is denoted in biased form. Now, the true exponent can be retrieved from the biased form if from the biased exponent we reduce the bias only. And finally, the floating point numbers are stored in the following way, that is, we have the first bit, that is the MSB, denoting the sign. Thereafter, we will have some bits for exponent, that is the biased exponent. And finally, the last field will be dedicated for the mantissa part. Therefore, if we specify n bits for the storage of the floating point numbers and say for the exponent field we are using k bits, in that case, the mantissa field will be of n minus 1 minus k. Now why this one? Because the sign bit is taking up the first bit place, isn't it? Now coming to the biased exponent, that is this exponent field, since k bits are being used, the range of the exponent is going to be 0 less than equals to exponent less than equals to 2 raised to the power k minus 1. And clearly the bias will be of 2 raised to the power k minus 1. So this is the summary of the representation of floating point numbers. So in this session, we observed a series of linked problems first, and thereafter we observed the summary of floating point representation. Alright people, that will be all for this session. In the next session, we are going to learn about the IEEE standards for floating point numbers. So I hope to see you in the next one. Thank you all for watching.